So last time we were talking about eigenvalues and eigenvectors, right? So the geometric meaning of eigenvector is really that if your vectors is the direction of the vector is unaffected by the transformation, then that is the eigenvector, right? So that is, if you do a transformation on a vector and then the result is that the vector is just multiplied by a number, but without changing the direction, that is the eigenvector. Of course, that number can be negative. That means that the vector can change to the exact opposite direction, but still that is considered to be the eigenvector. Okay. So, and I introduced the standard procedures of how to find eigenvectors and also eigenvalues, right? So for matrix, for any transformation matrix. Okay. So here and last time I also show you different cases where sometimes I do have, right, for 2x2 matrix, right? So sometimes I do have two different eigenvalues, right? So sometimes I have just one eigenvalues. So, but in fact, I can also call them two, but they are just the repeated roots, okay, from the quadratic equation. But and then sometimes you do have just the complex value for the eigenvalue, right? So here, the next example, I actually want to focus on the case where I have the repeated eigenvalue, right? So what I have here is that I have a 3x3 matrix, okay? So and then we are going to find the eigenvalues and eigenvector. Right? So for this matrix, we can see that there are not three distinct eigenvalues. Okay, so if you are go ahead and expand this determinant, right, of course, you're going to have a cubic equation, and then we'll see that we have either the eigenvalue to be 3 or 2. Okay, just two eigenvalues, right? So, and the 2 is the repeated roots. Okay, so for the this cubic equation. Okay. So now we want to try to find, okay, so the eigenvectors, okay, so for this problem, okay. So to find the eigenvectors, so again, right, we need to do it, consider the different case for the eigenvalue individually, right? So we need to consider two cases, right? So the lambda equals 3 and the lambda equals 2. So the focus of this example is actually on the lambda equals 2 case, right? Because this is the one that we have this so-called repeated root. Okay. But just as a practice, okay, so let's go with the lambda equals 3 first. Okay, so for lambda equals 3, okay, so if we go ahead and plug in this value back to the system, right? So what you have is the following, right? So here we'll call the eigenvector to be this one. Okay. So if we put lambda equals 3, then the system becomes this. So, and then if I just put it in, you can see that I have 3 equations, right? But then the third one does not give me anything, right? So the third one just tells me that 0 equals 0. Okay. And then the first one and the second one just gives minus x1 equals minus x1 plus x3 equals 0. And then the second one just gives me minus x2 plus x3 equals 0. Right. So the last one is just 0 equals 0. And that means, right? So then that means this x1 has to be equals to x3. This x2 also need to be equals to x3, and then x3 can be a free parameter, right? So which I call this c. Okay, c is a free parameter. So and that's why your x1 and x2 end up also being the same c. So that is, right? So then your eigenvector is written like this. So of course you will drop the c, right? So you just tell me that this 111 is the eigenvector that is corresponding to this lambda equals 3, right? So now the case that I want to focus on is actually the lambda equals 2. Okay. So if you go ahead and plug in lambda equals 2, okay, back to the system, okay, what you realize is that you have these three equations, and then tells you that x3 equals 0. But x1 and x2 can be anything. So basically, there's no any requirement on x1 and x2. So then I can just call this x1 to be c1, and then this x2 to be c2, right? So then that means your eigenvectors looks like this, like c1, c2, and then 0. Right? And it can be written like this, like c1 1 0 0 plus c2 0 1 0. So c1 and c2 are really two independent free parameters, right? So and now your eigenvectors is any linear combination, right? So of these two vectors, right? And you might notice that, right? So basically, these two vectors will span the whole xy plane, right? And in this case, right? So, but I will still, that means technically, right? So any vectors on this xy planes are the eigenvectors, okay? But at the end of the day, I will just tell you a basis set, okay, that represent this plane, okay, to be the two eigenvectors. So that's why this 1 0 0 and 0 1 0. And you will also be able to pick any other two vectors which are linear independent to be representing the plane, right? So as long as the two vectors span the xy plane, right? So then, for example, you can write it this way, right? This one is the same as this. Right. So then you can actually also tell me that you can also pick 1 1 0 and 1 minus 1 0 to be the two eigenvectors. Or, right, so you can, for example, just one more, is that you can also write it this way. Right. So this set completely equivalent to this set, also completely equivalent to this set. Okay. So just pick any set that you think is more convenient to work with, and then tell me that they are the two eigenvectors, right, corresponding to this repeated eigenvalue. Okay. So the case that we have this more than one eigenvectors corresponding to the same eigenvalue is known as the degeneracy. Okay, we'll say that these two eigenvectors are degenerate. Okay, so that means they correspond to the same eigenvalue. And because we have two eigenvectors that correspond to the same eigenvalue, so we say that there's a twofold degeneracy. Okay. Right. So that means, right, so this is the special case, right? So when you see this repeated eigenvalues, so you need to be careful. And in fact, it's not always the case that if you see repeated eigenvalues, then you are able to find the two degenerate eigenvectors. Sometimes they don't really exist like this way. I'll give you an example later. So here are some general properties about eigenvalues and eigenvectors. Okay. So is that, suppose if I have a matrix that have this set of eigenvalues, then A plus Qi, which is just another matrix, Q is just a number, then the eigenvalues is given by lambda 1 plus Q, lambda 2 plus Q, and so on. And if you take A inverse, okay, so the eigenvalues are actually just the inverse of all these numbers. Okay. Of course, provided that the A inverse has to exist. So here, so you can see a list of them. But these are some properties. I'll try to. I'm not going to show you all of them. We're not going to prove all of them, but we can try a couple of them. Right. So for example, the second one. Right. So how do we prove that? Because actually it's pretty straightforward. Is that because I told you that this eigenvalue is given by lambda, right? So the matrix A. Then if I multiply both sides by A inverse, right, so then you have this. And then the left-hand side just become X itself, right? So, and then further, I put this lambda I to the left-hand side, right? So then you have this. Right. So, and this exactly tell you that the eigenvalues of A inverse is 1 divided by lambda I. Okay. So this is property number 2. So, and we can also try maybe this one, like the last one. What it tells you is that A and this P inverse AP have the same eigenvalue. So this P is any matrix. Okay. So for any matrix P. So of course, again, we require that the P inverse exists, okay, in order for this thing to make sense. So again, how do we prove this? Is that, so first of all, again, I write down this A x equals lambda x. And then I define another vector y, okay, which is given by P inverse x. Okay. I define a new vector y. So I can always do that, right? Because P inverse exists, so I can always define a new vector in this way. So that means x equals P y. So now, if I put this x equals Py into my original equation, then I would have A Py equals lambda I Py, right? And then I can multiply both sides, right? So by P inverse, then the P on the right-hand side will disappear. So then you can now see that P inverse AP Y is equals to lambda I Y. And that proves that, right? So the P inverse AP has the eigenvalues of lambda I, right? Which is exactly the same as this set of lambda. So, but of course, you can also see one thing is that the eigenvectors are not the same, right? So the eigenvectors of, if the eigenvectors of A is X, right? So then the eigenvectors of this P inverse AP would be Y, okay? And this Y is given by P inverse X. So you can try to prove the others also. Okay. So now that we have talked about many examples on this finding eigen values and eigenvectors. Okay, so and then next I'll talk about how do we use these eigenvalues and eigenvectors to do an operation which is known as the diagonalization of a matrix. Okay. So what it means is the following. Okay, so is that I give you a matrix, okay, a square matrix, n by n square matrix, and then I want to find another matrix, which is also n by n. The other matrix I call P, okay, such that this product, this P inverse AP, is equals to a diagonal matrix B. Okay. So the diagonal matrix means that only the diagonal elements in the matrix are non-zero. Right? So all the other elements are zero. So that is the diagonal matrix. Okay. So and this process is known as diagonalization. Okay, it's known as diagonalization. So and let's see how that works. Okay. So I have the n by n case in the next slide, but first just to again I'll start with this 2 by 2 case. Okay. So 2 by 2 case, so let's say I have a 2 by 2 matrix A. Okay. And then suppose I have this matrix, I have the two eigenvalues and eigenvectors. Right? So then let me just write A, this is some vector that I call V1, okay, equals lambda 1 V1. So this is just a column vector, right? And then I also have a V2 equals lambda 2 V2. Okay. Suppose I've already found the eigenvalues and eigenvectors for this matrix A, right? So okay, so then this is what I can write down. Now I can kind of combine these two equations into one, okay, by writing it as a matrix form. Okay. So the way I do it is that I'm going to put again, okay, so the matrix A over here, and then another matrix, which is also a 2 by 2 matrix, and that means it has two columns, right? So the first column is my V1, okay. And then the second column is V2. So then the right-hand side, okay, so I will have to put it like this. Lambda 1 times V1 as the first column of the matrix on the right-hand side, and then lambda 2 V2 as the second column on the right-hand side. Okay. Just make sure that you understand how this one get to this one. Okay. So I'm just combining the two formula together, okay, and put it in this matrix form. So now the the right-hand side, remember, so this itself is a 2x1 vector, this itself is a 2x1 vector, and then the right-hand side can be further written like this. The right-hand side can be written like this. Just try to do the multiplication yourself. You see how this one is indeed is this one. So now what do we have? I have this A times a matrix, A multiplied by this matrix equals to the same matrix multiplied by this diagonal matrix, right? So you see that the second matrix here is a diagonal matrix. So now I'm going to call this matrix. I'm going to call this matrix P. I call this matrix P, right? So that means this is also P. And this matrix here is a diagonal matrix, which I call D, right? So that means from this, I have AP equals PD. And that means P inverse AP equals D. So then we're done. Okay, so we succeed in doing this diagonalization. So now you exactly see how the eigenvalues and eigenvectors helped us, right? So because this D matrix, right? So the element in this D matrix exactly are the eigenvalue. And this P matrix here is constructed by the eigenvector. So that means there is a standard procedure of getting a diagonal matrix, okay, from any matrix. Okay. So of course, I will show you some examples that sometimes the matrix cannot be diagonalized. Okay, but let's say here, right? So in this case, if I have two different eigenvalues and two different eigenvectors, then it will be guaranteed to be possible. Okay. So, but here you see that, right? So you find the eigenvalue, find the eigenvectors, and then you can be able to write the matrix in this form. So of course, this is the 2x2 case. For n by n case, right? So the idea is the same, right? So this time I have this A times this matrix. This matrix now is not just have two columns, right? So but have n columns. So suppose I have this n eigenvectors. So this whole thing is an n by n matrix, right? So each column is constructed by one eigenvector. And then similarly on the right hand side, right? So I have the same matrix constructed by the n eigenvectors, okay, and then multiplied by this diagonal matrix, right? So again, you can see that the diagonal elements are given by the eigenvalue. Okay. So then again, you put this back to the left hand side, right? So you see that, right? P inverse A P equals this diagonal matrix. So, and I just told you that sometimes the diagonalization won't work. And when would that happen? Right. So it will happen, right? So when you don't have P inverse, right? If you don't have P inverse, then this procedure won't work. Right? And if you don't have a P inverse, okay, so when will you not have a P inverse? So you don't have a P inverse if some of these if the set of the eigenvectors are not linearly independent. If that happens, then this inverse not exist. But first, let's look at the case that the two eigenvectors are linearly independent and this procedure works. Right, so if I consider this 2 by 2 matrix, right? So if you follow the standard procedure, right? So you'll be able to find out that the eigenvalues is 1 and 6. And then suppose, okay, so from 1 and 6, you also solve for the eigenvectors already, right? So let's say, right, so x1, y1 is the eigenvector corresponding to the eigenvalue 1, and then this x2, y2 is the eigenvector that corresponding to the eigenvalue 6. So, and then after you got this, right, so you just write down this, right, A, P equals P, D, right? So this P matrix, right, so its first column is this first eigenvector. Second column is the second eigenvector. Right? And then the first eigenvalues here, second eigenvalues here. And then at the end, right, so you find out that this inverse P inverse times your matrix times P equals to this diagonal matrix. And the two elements, right, so are the 1 and 6. So then let's come back to the question again, is that I already told you the answer, right? Actually, is that actually not every matrix can be diagonalized. So that means some of them are not diagonalizable. Okay. So, and as I said, right, so this matrix, you need to have the eigenvectors to be linearly independent. So if you find the eigenvalues, and if you find that the n eigenvalues that you have are all distinct values, they're all different, then you don't need to worry. Then it's guaranteed that the n eigenvectors that you find will be linearly independent. So now, the case that you might need to worry is that if there are the so-called repeated eigenvalues, right? Just like the first example I show you in the lectures, then you need to check, okay, whether the matrix A still got n linearly independent eigenvectors. So then let's go. If I go back to this example here, right? So in this example, I do have repeated eigenvalue. So for the first eigenvalue, which is not repeated, of course, I got a eigenvector here, no problem. And then in this case, right, for the repeated eigenvalue 2, we are also able to find 2 eigenvectors. Right? So that in this case, right, so is everything still okay? Right, so we do have 3 linearly independent eigenvectors. Okay, you can check. Right, so this 1, 1, 1 is actually, and this 1, 0, 0, and 0, 1, 0. These 3 form a linearly independent set. However, sometimes it might not be the case. So, and this is an example. Okay, so this is an example where we have repeated eigenvalues. Okay, and also with this repeated eigenvalues, I'm not able to find 2 linearly independent eigenvectors. So if I just go ahead to solve it. Right, so first of all, right, so 3 minus lambda, 1, 0, 3 minus lambda. This determinant gives 3 minus lambda square equals 0. Right, so you see that your repeated eigenvalue, right, so lambda equals 3. And that would mean 3 minus 3 x plus y equals 0. And then 0x plus 3 minus 3 y equals 0, right? So, and these two equations tell us that y equals 0, and then the next one just tell me 0 equals 0. So that means the eigen vectors must have a 0 y component, okay? And there's no restriction on the x component. So that means I can write down x equals to some 3-parameter c. So that is the eigenvector we have is c0, which is c times 1 0. So then 1 0 is the eigenvector. Okay. But then this is really the only one that we can find. Okay, just one eigenvector. So then that means we are not able to find two linearly independent eigenvectors. And in this case, diagonalization won't work. Okay. So this matrix cannot be diagonalized. So next, I would like you to try and problem by yourself. Okay. So try to find the eigenvalues of this 3x3 matrix. Okay. And then we'll find that again you have a repeated eigenvalue. But this time, the repeat eigenvalues again give you two linearly independent eigenvectors. Okay, I want you to spend a few minutes to try this. Right, so let's find the eigenvalues. So although this is a 3x3 determinants, right? So but it turns out that it's actually easy to do because I have two zeros over there. So 5 minus lambda minus 1 0 minus 1 5 minus lambda 0. So of course, right? So since I have these two zeros, right? So I'll just expand this determinants using this column here, right? So then what you have is just 4 minus lambda times this 2x2 determinant. So, and that is 4 minus lambda times 5 minus lambda square minus 1. And this is 0. Then what I have is, right, so lambda equals 4 or 5 minus lambda equals plus or minus 1, right? Then that this also gives lambda equals 6 or 4. So 4 appears twice, right? So this is the repeated eigenvalue. So then let's put lambda equals 4 back to the system. Okay, so this time let me just use the augmented matrix notation. So then that's 5 minus 4 minus 1. Right, so this is the system now, and that is right. And you realize that all these three equations are saying the same thing, right? And all it tells us is that x minus y equals 0, and then 0 equals 0. That means I will say that, right, this z is a free parameter. Let me call this C1, right? And then this x equals y, right? X minus y equals 0. That means x has to be equals to y. But that means x equals to y, but they can be anything also, right? So as long as they are equal. So then I'll just call x equals y equals to another free parameter C2. So then that means my eigenvector would be both x and y are C2, so C2, C2, and then C1. And you can write it as C1 0 0 1 plus C2 1 1 0. So now you see that the two eigenvectors, the two possible choices, right? So 1 1 0 and 0 0 1. Again, as I said, you can pick any other two eigenvectors which lie on the plane, okay, formed by these two vectors. And if you go ahead and also do the lambda equals 6 case, okay, which I won't repeat the whole calculation one more time, but for the lambda equals 6 case, okay, so you should be able to find that the eigenvector is this. And in this case, okay, we again have 3 linearly independent eigenvectors. And if you want to diagonalize this matrix, you can do that. Okay, so that's the end of this part of the chapter. Okay, so now let's take a 10-minute break, and then we'll go ahead and move on to the next part of the chapter. So let's come back at 12:28. Okay, so here comes to part 3 of this chapter here. So in part 2, we learn about how to do linear transformation for vectors, right? So, and it's basically mathematically is expressed as a matrix vector product, right? So rotation, reflection, scaling, and all that. Okay. So in this part of the chapter, we are considering something slightly different, which is the linear transformations of the coordinate system itself, or the basis vector. Okay. So, and mathematically, again, we are still going to play with the matrix vector product. Okay, but we need to be clear about the geometric interpretation. Okay, so the math procedure is quite the same, but geometric interpretation different. Okay. So first, let's remind ourselves about the connections between coordinate systems and basis vectors. Okay. So here you can see that I have the most simple case where I have this two-dimensional coordinate system, right? So the two-dimensional Cartesian coordinate system, right? And then I have all these grid lines, right? And suppose I have this point P here, okay? And if I say that this point P, okay, has a coordinate xy, okay, what it really means, okay, is the following, okay, is that we need to remind ourselves that this 2D Cartesian coordinate system is in fact constructed by these two unit vectors. Okay, I call this E1 hat and E2 hat, but you know that they're just X hat and Y hat, right? So so then the E1 hat is the one that go horizontal, and the E2 hat is the one go vertical. So when I say that I have a point P which has a coordinate xy, okay, so what it really means is the following, right? Is that suppose you start from the origin point O, right? So take x steps, right? So along the directions of this E1, the first basis vector, and then takes y step, right? So along the direction of the second basis vector E2, right? And the length of each step, okay, so would be equals to the length of each basis vector, which is unit vector, right? So this one. So, and that means when I tell you this coordinate of P is that xy, okay, so really, strictly speaking, okay, you should ask one more question, is that what are the basis vectors? Right? So because the x and y themselves, okay, so do not actually contain the absolute position of this, right? So you need to really ask, okay, so what is this E1 and what is this E2? right? So then you know that x means that you walk along this E1, right, for x step, right? Y means walk along this E2 for this Y step. Right? But of course, in the Cartesian coordinate system, so everything is well understood, right? So this is just one along the horizontal direction for each step, and then one along the vertical direction for each step. So we don't really write down the basis vector out, right? So every time when we use this coordinate system. So now, if suppose I have this position vector v, okay, so which is the position vector of this point P. Okay. So, and this v is a physical quantity, right? So I'm talking about the position of this point P. Okay. And that means this v is coordinate independent, actually. But of course, I still need to define the origin point O, right? So I need to, if I fix the point O, right? So then I'll just always be able to tell you that this is the V, right? Even without all the grid lines behind, right? So this is the V. Right? So, but anyway, if I use these two basis vectors, okay, to express this V vector, right? So then I will be telling you that V is equals to X times E1 hat plus Y times E2 hat, right? And here we just express this E1 as 1, 0, and this E2 as 0, 1. Right? So then this V is just this one. So now suppose what we try to do is to consider another coordinate system. Okay. So the one on the left, right, is the one that I just showed you in the last slide. So now there is another coordinate system, okay, constructed by another person, another observer, let's say. Right. And then the the unit vectors or the basis vectors that the other observer used is this E1 prime and E2 prime, okay, instead of this E1 and E2. Then here you can see how these coordinate grids are different from what we had before, right? So because this set of grid lines, right, so goes along to this E1 hat, and the other set of grid lines go along the E2 prime. Okay. So, but one thing that is not changed is that suppose the origin, okay, the origin, we define the same absolute point in space as the origin. Okay, so the origin point is the same position. So really, what you should try to do is try to, in your mind, okay, overlap the two picture together. Okay. So now we are still talking about the same position vector v, right? So as I said, this position vector v is a physical quantity and is coordinate independent. Right? However, you can see that if I use the coordinate system A, then I will tell you that v is equal to x E1 hat plus y E2 hat. If I use the coordinate system B, okay, so I'll tell you that this P, this position vector V is given by x prime E1 hat prime plus y prime E2 hat prime. Right? So, and numerically, right, so this x is not equal to x prime, and this y is not equal to y prime. Okay. So that means if you have using this coordinate system, right, the coordinates are actually different. Okay. Although really physically, right, so these two P are at the same position. So let me give you some concrete numbers, So in this case, what happened is that if you actually go to put these two new unit vectors, okay, into our original coordinate system, that means this put this E1 prime in here, I put this E2 prime over here, and express this E1 prime and E2 prime in terms of our basis vector, okay, then you will, right, so find this relations here, okay. So you can see that, right, so E1 is going to the right, but also a little bit to the up, so that then that is given by this E1 hat plus 1/2 E2 hat. So, and then for this one, right, so it's given by this minus E1 plus E2. So now we know that, okay, so suppose this point P in this original coordinate system is at the coordinate 3, 3. So that means in this coordinate system, I will tell you that V is given by 3 E1 hat plus 3 E2 hat. So now, what about coordinate system B? Right. So coordinate system B is V is expressed like this. But what are X prime and Y prime? So this is our goal. Okay. So this is the coordinate transformations that we are trying to achieve here. Right. So I tell you the relations between the two sets of basis vector, okay, over here. And then I tell you the vector expressed in one of the coordinate system. And then I want to know how we can express the same vector in the other coordinate system. In fact, okay, here, if you look at the grid lines, okay, you know the answer already. What is this in this coordinate system? That is 1, 2, 3, 4. 4 steps over here, and then 1 step up here. So X prime is 4 and Y prime is 1, right? As opposed to here is 3, 3. So, but okay, so we'll actually do it, right? So systematically, okay, using the algebra. So we are standing in coordinate system A, right? So from our viewpoint, right? So I call E1 to be 1, 0 and E2 to be 0, 1. Right? And then we'll also say that, right? So E1 prime is this one, right? So because just using these two relations, I'll say that E1 prime is this vector, and then E2 prime is this vector. And now, as I said, right, so physically, so V is coordinate independent, right? So that means that this 3E1 plus 3E2 has to be equals to X prime E1 prime plus Y prime E2 prime, right? So our goal is to find out this X prime and Y prime. So then this is a vector equation, right? So then I just write it this way. Now, I just make the left-hand side to looks like this matrix vector product. Also, the right-hand side looks like this matrix vector product. Right? So then the unknown is over here, X prime and Y prime. So now we want to know X prime and Y prime, right? So basically we just take the inverse of this, right? Put this matrix to the left-hand side, right? So and then you find that X prime, Y prime is indeed 4, 1, right? So as what you expect from this graph here. So let's summarize, okay, what we just did. A transformation of the coordinate can be expressed as a matrix equation like this, right? So transformation of coordinates, or we sometimes call it the change of basis, right? Is that right? So these two refer to the same vector, right? And then this is expressed in terms of the coordinate system A, and this is expressed in terms of the coordinate system B. Right? And if right, so in one of the coordinate system, right, so we just set this two basis vector to be 1, 0, 0, 1. So this is really just an identity matrix. So and that means the transformation is given by this equation here. We do the inverse, right? So then this x prime, y prime is given by the inverse of this matrix multiplied by this column vector xy. So now you can see that transformations of the coordinates again can be represented by a matrix. In the part 2 of this chapter, right? So we also see that transformation of the vector itself is also represented by a matrix. So, but in that case, we are actually changing the vector, right? So here, right? So the vector itself is not changing, right? Just the coordinate system changes or the basis changes. So then this is the geometric meaning that you need to remind yourself that they are different. Okay, so both transformation of vectors and transformations of coordinates or bases, okay, are represented by matrices. Okay. But the geometric meaning different. So and in particular, we will be focusing on the linear transformation. Okay. We'll be focused on things on the linear transformation. Okay, so and the linear transformation has the following property. Okay, so is that if you have an original coordinate system, okay, so they have two set of grid lines, right? So after the linear transformation, the two set of grid lines, okay, so they change direction, the directions, and also the spacing might change. However, it's still a set of two sets of parallel straight lines, okay, here and here. Okay. And also, the spacing between the nearest parallel grid lines, okay, will remain to be uniform. The spacing, right, so between the two grid lines really means that you take one step, right, so along the direction of one of the basis vector, right? So and here you can see that, right, so this spacing equals to this spacing equals to this spacing, right? So here, right, so this spacing equals to this spacing equals to this spacing, and so on, right? So if this is a linear transformation, right, so this is the property. And also the position of the origin, okay, will remain unchanged. Okay. So that means geometrically you can kind of think of like you can take the grid, stretch it, but the stretch has to be uniform, okay, and you can also rotate it, okay, but then at the end you cannot bend the grid lines themselves. Okay, so they are still all parallel straight lines. Okay. And again, so mathematically, right, so as you've seen already, this transformation can be represented by a matrix. So an example of this transformation, which is not linear, is this. Okay, this is the one that we actually use a lot. Right? So if you go from Cartesian coordinates to polar coordinates, so this is actually not a linear transformation, right? So because if you relate the coordinate variables, right, in this form, you cannot write it as a matrix, right? So that has xy column vector on the one side and then alpha theta vector on the other side. You cannot write it as a matrix. This is an example of a nonlinear transformation. So now let's do one more example of linear transformation, okay, between two coordinate systems. So this time, the transformation that I'm doing is a rotation of the coordinate system. Again, okay, I have this v vector, okay, which is physical quantity, not changing, not depend on this coordinate system. Right. So this black x and y axis, okay, so represent the original coordinate system. So, and then after rotation, okay, so clockwise, so then I get this coordinate system B, which is given by this x prime and y prime axis. Okay. So first, right, so I want to relate the basis vectors of the two coordinate systems. So before transformation, right, so my basis vector would be this E1 and this E2, right? This is the basis vector for the original coordinate system. Okay. So after the rotation, right? So then this will be my E1 prime, and this is the E2 prime, right? So from the geometry, okay, you can relay this E1 prime, right? So with this E1 and E2, right? You can also relate this E2 prime with this E1 and E2, right? So because if I try to just draw E1 again here individually, E1 prime, sorry, then you will find that this length here, this is cosine theta, right? And then this length here is sine theta. Because again the length of this E1 prime is still 1, right? So that's why this component is cosine theta, is sine theta. So that's why this E1 prime can be written as cosine theta E1 hat, okay, minus sine theta E2 hat, right? Because this is going to the negative of the opposite to the E2 direction. Right? So then you see that, right? So this E1 prime equals to cosine theta E1 minus sine theta E2. So similarly, right? So you can express your E2 prime in terms of E1 and E2. So now in the original coordinate system, right? So my E1 and E2 are represented by this 1, 0, and 0, 1. Right? So then in that case, right? So using this relation here, you'll find that E1 prime is given by this column vector cosine theta minus sine theta, right? And then this is the E2 prime. So and therefore, right? So the coordinate transformation, right, is given by this matrix vector product, right? Just following this formula here, right? Following this formula here is the inverse of this matrix. So now, of course, you see that this looks, right, so exactly like a rotation matrix for a vector. However, if you rethink, okay, what it means in the last part of the chapter, right? So when we have this matrix, it means the rotation of a vector by theta anti-clockwise. So, but here you can see that we are rotating the coordinate system by theta clockwise. So, and what it really tells you is that, right, so rotating the coordinate system clockwise is equivalent to rotating the vector counterclockwise. And geometrically, that's not difficult to think about, right? But anyway, so this is the thing that we are talking about here. Okay, so it's a rotation of the coordinate system. Okay, not the rotation of the v vector itself, right? The v always points to this direction. V itself not rotate. So now we know how to transform. Okay, so one coordinate system to another. Okay. And then next, what we want to learn is that how do I express a transformation matrix in two different coordinate systems. So just now we learned how to express the same vector in two different coordinate systems. Here I want to express the same transformation matrix in two different coordinate systems. So, but what does that mean? So first of all, right, so the transformation matrix here, okay, so again, I am referring to the matrix that actually help us to transform a vector. You need to go back and think about what you had in the last part of the chapter, right? So now that means now I actually want to change the vector. Okay, just like a rotation of a vector. Okay, just like this picture. Okay, this picture. So look at this picture first. Okay, so this is I don't put any coordinate system in it, right? Intentionally. First of all, I don't put any coordinate system in it. I want to have some transformation, right? So from this v to this v prime. Okay, so this is the transformation that I'm going to I want. Okay, and then this is actually a rotation, right? So, and you know that if you are going to use the usual Cartesian coordinate system that we have, you know that this transformation can be written as, right, so this. So this is theta. Now, if I'm going to use this coordinate system instead, right? So, but I'm actually doing the same thing, right? So same rotation here. Okay. So how does this transformation matrix in this coordinate system B looks like? Okay. Okay, I hope it's clear. Okay. Right. So I'm actually changing a vector. Okay. In the usual Cartesian coordinate system, this transformation or this rotation is expressed like this. Okay. But if you are using this coordinate system B, okay, so the transformation matrix for this vector is no longer looks like this. Okay. Looks like something else. And we want to find out how to get this form of this transformation matrix, okay, from this one. Okay, so that's rotation of this vector is something you have in mind. That's good. So it doesn't have to be rotation, right? So it can be other things. But so let's say in general, right? So I have a vector v that is coordinate independent, right? So this one. So now I put this vector v in this coordinate system A. So I denote this as this v subscript A. Okay. And then I denote this TA, okay, so to be a transformation matrix that transform this VA to VA prime. So, and at this point, that means I'm doing the thing on the left-hand side. I'm doing this rotation or this transformation. I have not yet talked about any change in coordinate system yet, right? So up to this point. Okay. So now, right, so I want to, as I said, we express the same transformation process in this coordinate system B. Right? So, and mathematically, so that means that in the coordinate system B, we go from VB to VB prime. Right? So using some transformation, this TB. So in the previous slide, we have this VA prime equals VA. Right. Remind you one more time, right? So the form of these two matrices, this TA and TB will be different. Okay. But both of them represent the same geometric operation. So a few slides earlier, right? So we have already learned that this VA and this VB can be related by this matrix equation, right? So this VB equals to P inverse A, which is in this slide here, right? So I'm using this formula here. So VB equals P inverse A, VA, right? And this P inverse represented the change of basis. So now that means I put this back to this equation here. I put this relation back to this equation here. Then I will have P inverse VA prime equals TB P inverse VA. And then I also put this P inverse to the right-hand side. Then I will obtain this VA prime equals to the product of these three matrices, okay, multiplied by this VA. And this whole thing has to be TA, right? So this is what we had in the last slide. So therefore, right, so the transformation expressed in coordinate system B is equals to P inverse T, the same transformation expressed in coordinate system A times P. So then I actually use this rotation to do the example, right? So as I come back to this question I asked in the beginning, in the coordinate system A, the rotation matrix right like this. What about in coordinate system B? So, and you realize that if you actually use this formula, P inverse TAP, the rotation in coordinate system B looks like this. Okay. But really, this one in this coordinate system, right, is doing the same rotation as this one. So now, when you see this P inverse TAP, it might remind you of the formula of diagonalizing a matrix, right? As I showed you earlier today, right? So, and now let's talk about diagonalization again, right? Right. So, in general, or most of the time, a transformation matrix T is not a diagonal matrix, right? So just like rotation, right? Scaling is a diagonal matrix, right? So, but rotation is not a diagonal matrix, right? So many of the transformation matrix, okay, may not be diagonal matrix, right? So, however, right? So we have learned that if a matrix T can be diagonalized, so then that means there will exist a matrix P, right, such that this P inverse TP is a diagonal matrix. And also, right, so the P is the matrix whose columns are composed of the eigenvectors of T, right? So this is what we have just learned, right? So like an hour ago. So now, suppose, right, so I am in the coordinate system A, right, and then this TA is a transformation matrix that is not a diagonal matrix. Okay, let's say that. And then if I want to find another coordinate system B, okay, such that the same transformation but expressed in that new coordinate system is a diagonal matrix. Right? So that means, right, so we if we refer to this, right, so we want this TB to be a diagonal matrix, right? Although this TA is not. And now you know that how do we do that, right? So is that if this P, right, if this P is constructed by the eigenvectors of this TA, so then this TB will be a diagonal matrix. So, and then why do we want this to find such a coordinate system where the transformation matrix is diagonal? So it is because calculations with diagonal matrix are much easier, right? So if you have the vectors, you want to transform it, right? So you just need to multiply it by a diagonal matrix. That's very easy, right? So then example here, right? So is that suppose I have this transformation matrix, okay, like this, right? So in a coordinate system with this two basis vector, right? And then you know that this eigenvalues and eigenvectors of this matrix, right? So it's given here. So then in a coordinate system where the basis vectors are just given by the eigenvectors of the TA itself, right? So then the transformation, okay, will just be given by a diagonal matrix like this. Okay.